I wanted to take a few minutes and show you where the range equation comes from. The textbook says that if the launch height and the launch landing position are the same, so delta y is equal to 0, and you always launch at the same speed, then you can figure out what the range is going to be. Here I've written it as delta x as a function of the launch angle. And they've got this strange sine times 2 times the launch angle function. So where does that come from? You don't technically need to know where it comes from, but I want you to know where it comes from. So I've drawn this picture. Here's my projectile. It's launching from y equals 0, and it's going to rise and fall and land over here someplace, and it will land at y final equals 0 meters. And then I've taken the liberty of decomposing the velocity vector into its x and y components, and so I've got the v naught y to be v naught sine theta, and I'm going to say I don't know how fast it's going when it strikes the ground in the vertical dimension, and I know it's free falling, so I'll put g here, and then the time is really what I'm looking for. So I'm interested in figuring out how much time this real projectile takes to rise up to its apex and fall back down again. But just following it in one dimension, I'm just looking at how it rises to its apex and then falls back down again. And this imaginary projectile is launched upward at whatever v naught y is. I'm purposefully not putting in numbers because I want this to be a general statement for any launch speed and any launch angle. So then my first goal is to figure out what the time is. I don't know what that final speed is, so I use the big dog displacement equation. And I look for things that are 0, like the launching position and the landing position. And I'm looking for the value of t that makes this condition of delta y being 0 true. So one of the things that I notice is I've got two terms, each with a factor of t in it. So my technique is to factor out a t, and then in order for these two factors to equal 0, one of the factors has to equal 0, like this first one here, or the second factor has to equal 0. And so I'm going to take 1/2 gt, subtract off v naught y, multiply by 2, and then divide by g. And that's the second time at which y final equals y initial. So I've got this position here at t equals 0 seconds, and then it lands in time over here with whatever time this calculates out to be. Now that v naught y is a symbolic placeholder for v naught sine theta. Okay, so now let me try to calculate what the range is going to be. So I use the big dog displacement equation again, but in the horizontal dimension. When we're free falling, the horizontal accelerations are always 0, and I'm going to start from x equals 0 at the very beginning of the launch. So I get x equals v naught x times t. So this t is whatever this t is. So I'm going to expand again. So v naught x is v naught cosine theta. And then here comes t. It's -2 v naught sine theta. And that's a valid expression right there for the range, but I'm going to clean it up a little bit. So I see a v naught factor and a v naught factor. So that's a v naught squared. And this g is in the denominator. What I'm going to do is, this g is -9.81, so I'm going to imagine for a moment the absolute value of that and kind of pull the negative out. And so that negative cancels with that negative there. And so the g I put down below here is really the absolute value of the acceleration. And then what I have left over, I've got a 2, a cosine function, and a sine function, that launch angle argument. So it turns out there's this thing called a trigonometric identity. It's pretty cool. It states that if you're multiplying 2 times the cosine of an angle times the sine of an angle, it's equivalent to the sine of twice the angle. You don't necessarily need to know that. You'll hopefully learn about it someday. It's called a trigonometric identity. Trig identity. And on your calculator, you can check to see if that's true. Just pick any angle and then multiply 2 times the cosine of that angle times the sine of that angle and compare it to sine of twice the angle. Turns out they're exactly equivalent. So that's what I'm going to do here. I'm just going to clean this up. That's all I'm using it for. This equation right here is the range equation, but I'm going to make it look a little nicer by substituting in that trig identity. Leave this here, and then I'm going to write sine of 2 theta. So there's that equation the textbook describes. It's kind of cool. That's the range equation. And it's valid when delta y is equal to 0. That's important. And then what I'm going to do now is just take a graphical look at that thing. And a little bit strange with this twice angle, so let me talk about what's going on. This peak part right there, that's the maximum range. And the sine function maximizes at 90 degrees. So when the angle of the launch is 45 degrees, 2 times 45 will give you 90. So that must be that this position right here is 45 degrees. And then this, if right here, is where the range goes to 0. So if I launch at 90 degrees, 2 times 90 is 180, and the sine of 180 is 0. So this is the 90 degree. That's a launch straight up in the air and straight back down again. Similar to the launch at 0 degrees. Excuse me. And then, strangely enough, if I keep going, so if I'm launching in the first quadrant, like 25 degrees, 30 degrees, 45 degrees, 60 degrees, 80 degrees, 90 degrees, I can keep going and go 110, 135, 165, and finally get to 180. I could launch all the way anywhere here above the ground, right? So that's what's happening here. If I continue to launch in these second quadrants, then this position on the graph shows me the maximum range, but to the left, and that's corresponding to 135 degrees. It's kind of cool. So twice 135 is 270, and that's when the sine function goes to -1, so it maximizes in the negative dimension. And then if I go here, 180, that would be like launching just perfectly leftward, and so it just smashes into the ground right away. And that's what's being predicted by that function. It's a beautiful thing. What we're noticing in our lab is that there's a maximum range at 45 degrees. We're focusing just on first quadrant launches here. And then the neat thing about this is also that if you draw a horizontal line, then you indicate, you kind of discover that there's 2 launch angles that would achieve this range. Whatever that range is right there, that's going to correspond to this launch angle and to this launch angle. And those, by symmetry, these angles that are equidistant below and above 45 degrees, that right there and that right there, those angles are complementary angles. So theta plus phi equals 90 degrees. So it's telling us that for this type of a launch situation, you can launch at the same speed, but twice 2 different angles to achieve the same range.